Can one carefully chosen function rule out every denser sphere packing? OpenAI's Astra release reports 10 advances, but we will not start with the headline. We will test the Cohn-Elkies certificate on a square lattice, watch one pair sum acquire a ceiling and a floor, and then see why a 1/pi mass barrier controls the high-dimensional answer. Keep 4 layers separate as we go. OpenAI says the internal model generated the arguments. Humans prepared the manuscripts with it. The model formalized the arguments in Lean, and the public papers and repository can now be inspected. Discovery, manuscript, machine checking, and independent review are not the same claim. The collection spans 10 areas. We will fully understand one sphere packing certificate, then orient each remaining result with one concrete bottleneck, one change of representation, and one reported outcome. Those final cards are a map, not 9 pretend proofs. Sphere packing asks how densely identical balls can fill space without overlapping. In 2 dimensions, think of coins on a table. In 3 dimensions, think of oranges in a crate. In dimension 100, we cannot picture the balls, but distance and volume still make sense. The challenge is not finding one packing. It is proving that no possible packing can be denser than a certain limit. Scale the picture, so every pair of centers is at least distance 1 apart. Then every packed ball has radius 1/2. Call the supremal density in dimension d, delta d. A direct search over every arrangement is hopeless. The Cohn-Elkies method replaces that impossible search with a certificate, one carefully chosen radial function that every packing must obey. Choose a smooth, rapidly decaying function f that depends only on distance from the origin. It must be non-positive once the radius reaches 1, exactly where distinct packing centers are allowed to appear. Meanwhile, its Fourier transform must be non-negative at every frequency. One function is pessimistic in physical space and optimistic in frequency space. Those opposite sign rules let us trap the same quantity from both sides. Start with a periodic packing. Suppose one repeating cell contains n centers and the lattice cell has volume called covolume. Now sum f over every ordered pair of centers, including all translated copies. Call the result S. This is not a random statistic. S is engineered so that distance separation controls it in physical space, while Poisson summation controls the very same S in frequency space. When a center is paired with itself, the displacement is 0, so the term is f of 0. There are n such diagonal terms in each cell. Every other pair is separated by at least 1, where f is non-positive. Those off-diagonal terms can only pull the sum downward. Therefore, S is at most n times f of 0. That is our physical space ceiling. Poisson summation rewrites the same pair sum as samples of the Fourier transform on the dual lattice. Every one of those samples is non-negative. Keeping only the zero frequency term already gives a lower bound. S is at least n squared times f hat of 0, divided by the cell covolume. Nothing mystical happened. We changed accounting systems, and the sign rule reversed which direction was useful. Now squeeze. The frequency space floor cannot exceed the physical space ceiling. Rearranging bounds and divided by the cell volume, which is the number of centers per unit volume. Multiply by the volume of a radius 1/2 ball, and we get the Cohn-Elkies certificate. Delta D is at most the unit ball volume times f of 0, divided by 2 to the d times f hat of 0. Before touching the new high-dimensional result, test the logic in 2 dimensions. Take f of r equal to 1 minus r squared times e to the minus pi r squared. At the origin it equals 1. At radius 1 it reaches 0. Beyond 1 it is negative, and the Gaussian makes it decay rapidly. So the physical space sign rule is visible directly from the curve. Under the paper's Fourier convention, the transform is rho squared plus 1 minus 1 over pi, all times e to the minus pi rho squared. The smallest value of the polynomial factor occurs at 0, where it is 1 minus 1 over pi, still positive. So this toy function satisfies both sign rules. It is a genuine certificate, not an illustration that merely looks similar. Put the function on the square lattice. Summing the physical space values over a 17 by 17 patch gives 0.9924835585151. Summing the Fourier values over the matching frequency patch gives the same number to 12 decimal places. The omitted Gaussian tails are already tiny. This numerical equality is Poisson summation made concrete. Now for an important failure. Insert this toy function into the density formula, and the upper bound is about 1.152. A packing density cannot exceed 1 anyway, so the result is useless. The proof logic is valid, but the chosen certificate is weak. Research begins where classroom verification ends. Optimize the ratio f of 0 divided by f hat of 0 without breaking either global sign condition. The paper's first change of perspective is to stop treating that origin ratio as an awkward number. Rescale an admissible function until the values of the function and its Fourier transform match at the origin. Call the rescaled function h. Then subtract h from its Fourier transform. The new function g has a much cleaner identity. Fourier transforming g flips its sign. Because the origin values were balanced, g is 0 at the origin. Because the original f was eventually non-positive while its transform was non-negative, g becomes non-negative outside a radius r. And r is exactly the dth root of the original ratio f of 0 over f hat of 0. Optimizing the packing certificate has become a geometric question. How close to the origin can an anti-Fourier function become permanently non-negative? The source also proves that g is not the 0 function. Its integral equals its Fourier value at 0, which is 0, so the positive and negative sign masses cancel. Once g is non-negative outside R, every negative contribution must live inside that ball. Exactly half of the L1 mass of g is negative and must fit there. Can that half squeeze into a very small central ball? For a radial function, the Fourier transform is a Hankel transform built from Bessel functions. That is still difficult in high dimension. The decisive move is a Mellin transform, which is Fourier analysis on logarithmic radius. Concentric shells become positions on a line. Under this transform, the radial Fourier operation becomes a reflection, multiplied by an explicit ratio of gamma functions. Geometry has been converted into complex analysis on a strip. Why exactly 1 over pi? Near the upper edge of the Mellin strip, the relevant harmonic measure distribution approaches a logistic density. Its logarithmic potential can be evaluated exactly. The sign flips when c equals 1 over pi, turning that constant from a numerical guess into the sharp boundary of the strip estimate. The estimate is relative. When c is below 1 over pi, only an exponentially small fraction of the L1 mass of a non-zero radial anti-Fourier function with g of 0 equal to 0 can lie inside c times square root d. Our balanced g needs exactly 1/2 of that mass to be negative inside R. Therefore, R is at least 1 over pi times square root d, up to lower order error, for every admissible certificate. A lower bound on every certificate is only half the theorem. To prove the constant is sharp, the paper also constructs functions that approach it. A Gaussian is the natural starting point because its Fourier transform is another Gaussian. In Mellin space, a carefully chosen negative deformation shifts the saddle point until the sign change occurs at the predicted radius, 1 over pi times square root d. The ideal deformation fails globally. It is singular near 0 and cancels too much Gaussian damping. The repair lives in Mellin weight space. Truncate and taper the negative weight, then add a much smaller positive weight on a remote interval. Near the target, it changes almost nothing. Far away, it dominates dangerous oscillations and restores damping on the unbounded saddle branch. Small radius positivity still needs a separate argument. The construction uses a Fourier paired family. One member, f-, becomes negative beyond the target radius. Its Fourier partner, f+, is positive in the large radius regime. The paired Mellin design preserves the exact Fourier relationship, while the saddle analysis establishes the required exterior signs. The saddle estimate says nothing near the origin. A separate contour shift crosses finitely many gamma poles and expands F plus into a controlled positive series with a negligible remainder that closes the small radius gap. After rescaling, the matching family has sign radius divided by square root d approaching 1 over pi asymptotically. High-dimensional unit ball volume is governed by Stirling's formula. Combining that volume with the 1 over pi radius gives the Cohn-Elkies program's rate. The dth root of LPD approaches the square root of e over 2 pi. Therefore, delta d is at most 2 to the minus 0.604400544 plus lower order error times d. The classical exponent was 0.59905576. A larger exponent means a stronger upper bound, not the exact packing density. The released manuscript calls this the first improvement since 1978 to the general sphere packing exponent. It also proves a ceiling on the method. No Cohn-Elkies auxiliary function can improve the leading exponent beyond this value. That does not identify the exact optimal packing in every dimension. It says this powerful Fourier linear program has now been understood at leading exponential order. In binary coding, strings are kept far apart so errors can be corrected. Spherical codes keep points separated by angle. Classical bounds kept one fixed harmonic direction at each degree. The new argument attaches a moving harmonic subspace to each code word and keeps the full positive gram remainder. For binary relative distance between 0 and 1/2 and spherical maximum inner product between 0 and 1, the reported upper bound exponents improve the classical benchmarks. A sophic group is one whose finite pieces can be approximated by permutations of finite sets. Whether every countable group was sophic had remained open. The construction combines property T expanders with two self-similar compressions inside a binary Leavitt algebra. The compressions force many expanding components to line up into one. That would make a known non-LEF subgroup look locally finite, a contradiction. The manuscript constructs an explicit non-sophic group. Conus's conjecture asked whether an ICC group with Kasdan's property T is determined by its group von Neumann algebra, roughly an operator algebraic shadow. The construction gives infinitely many pairwise non-isomorphic, finitely generated ICC property T groups with isomorphic factors. A characteristic 2 quadratic carry changes torsion. Some groups contain order 4 behavior while others do not, while preserving the measured action that generates the factor. The permanent looks like the determinant with every sign made positive, and proving arithmetic circuits need many operations is notoriously hard. The manuscript tracks where the gradient can vanish through a critical cone, retains matching structure, and uses root of unity cancellation to pack many coefficient blocks into one permanent. It reports omega of n squared log n gates for division-free circuits and omega of n to the fourth over log n variable leaves for formulas. If players have less than perfect success in one game, repeating it should make winning every copy exponentially unlikely. Entanglement makes that classical intuition difficult because conditioning can distort probability and quantum phase. The new proof introduces a resolvent purification that preserves Born weight, then uses a live coordinate martingale and correlated sampling. The reported theorem gives exponential repetition for every finite two-player, one-round entangled game. The closest vector problem asks for the lattice point nearest a target, a foundational problem connected to post-quantum cryptography. A reduction from 3 SAT must make local clause choices agree on one global assignment. The manuscript uses characteristic 2 moment tables, Hankel reconstruction, and a parity lift lattice. Through a deterministic polynomial time reduction from 3 SAT, it proves NP hardness of Euclidean closest vector within factor and to the 1 over 400. Take a convex body whose center of mass is the origin and whose only interior lattice point is that origin. How large can its volume be? The sharp answer is the volume of a particular centered simplex, quantity n plus 1 to the n, divided by n factorial. The proof changes settings completely, representing an arbitrary convex body through a toric Mons-Ampere potential. Lattice jet counting supplies one slope, Bergman kernel positivity supplies convexity, and a shrinking complex ball supplies the matching upper slope. Color every edge of a complete graph with one of k colors and try to avoid a single color triangle. Fixed graph products could not make the exponential base grow with k. The new construction glues carefully separated palettes using saturated matrices and a recursive cross-edge rule. It answers the superexponential question. The kth root of Rk of 3 tends to infinity. Indeed, Rk of 3 equals k to the theta of k. It does not determine an exact limiting base. The 10th headline contains two separate extremal graph results. For compactness, the construction uses incidence graphs from different finite fields so each forbidden graph has its own dense witness, while the whole family forces a smaller exponent. For degeneracy, a thinned Hamming cube host and an entropy potential build a fixed two-degenerate bipartite graph beyond the conjectured exponent. In both cases, the counterexample appears only after choosing geometry that matches the quantifiers exactly. Across many of the results, a useful pattern is not ask a chatbot for a proof. First formalize the bottleneck. Then change representation, geometry to Fourier and Mellin space, fixed harmonics to moving subspaces, clauses to moments, convex bodies to toric potentials, or colors to palettes. Where the theorem calls for it, prove an obstruction and build a matching witness or counterexample. Finally, translate the result back into the original language. The public repository contains Lean formalizations for the selected results and can be checked by Lean's kernel under declared axioms, including propositional extensionality, classical choice, and quotient soundness. That is strong evidence about the formal derivations. But the manifest labels the review status agent reviewed. Lean does not decide whether an informal theorem statement perfectly captures every headline, whether attribution is complete, or whether the community agrees on significance. So the interesting story is bigger than a model name and smaller than magic. OpenAI reports 10 research advances from an internal Astra system, with manuscripts and formal artifacts released for inspection. One of them turns an impossible search over high-dimensional packings into a two-sided Fourier certificate, finds a 1/pi mass barrier, and constructs a matching family whose sign radius approaches it asymptotically. The right response is neither instant belief nor dismissal. It is to open the proof, reconstruct the mechanism, and check what the artifacts actually establish.